Nobody expected the announcement to come from Changchun. That is the first thing to understand about what happened and why it landed with the force that it did inside the semiconductor industry's most closely watched boardrooms and policy offices. Changchun is a northeastern Chinese city better known for automobile manufacturing and film studios than for cutting-edge photonics research. It is not Eindhoven. It is not Silicon Valley. It is not the kind of place that appears on the mental map of people whose job is to track the frontier of semiconductor equipment development. And that, in retrospect, is precisely why what the Changchun Institute of Optics, Fine Mechanics, and Physics announced landed with such force. Nobody was watching Changchun closely enough. And the thing they announced, a domestically developed extreme ultraviolet light source capable of producing EUV radiation at the wavelengths required for advanced semiconductor lithography, is the one development that ASML's leadership had identified as the existential threat to its monopoly and had spent years arguing was too far away to worry about seriously. It is no longer far away, and the global semiconductor industry is still working out what that means. Why ASML sleeps uneasily. ASML's monopoly position is genuinely extraordinary. No single company in any technology sector holds a more complete and more strategically consequential monopoly over a critical input than ASML holds over EUV lithography systems. Every advanced semiconductor fabricated below roughly 10 nanometers, every cutting-edge artificial intelligence chip, every high-performance mobile processor, every advanced memory device requires EUV lithography to manufacture efficiently at commercial scale. TSMC uses it, Samsung uses it, Intel uses it. No serious alternative exists at the production frontier. ASML is not one of several options in a competitive market. It is the only option. Full stop. This monopoly did not emerge by accident or through anti-competitive behavior. It emerged through 30 years of sustained engineering investment in one of the hardest physics problems the semiconductor industry has ever tried to solve. Building a machine that generates extreme ultraviolet light, a form of electromagnetic radiation with a wavelength of 13.5 nanometers that is immediately absorbed by virtually every material, including air, that focuses that light through a system of precision mirrors onto a silicon wafer with nanometer scale accuracy, and that does all of this at a throughput sufficient to make commercial chip production economically viable, is an engineering achievement of almost incomprehensible difficulty. Every component is a decade-long research program. Every subsystem operates at the limit of what physics permits. ASML spent roughly 9 billion euros on research and development before its first EUV system entered volume production in 2017. The investment was so large and the timeline so long that at multiple points, serious industry observers argued the technology would never be commercially viable. It became commercially viable, and then it became a monopoly. And monopolies, as history consistently demonstrates, attract challengers. ASML's fear is not that a competitor will build a better EUV machine. Its fear is more specific and more consequential than that. The fear is that a competitor will build an EUV machine that is good enough, that functions at a level sufficient to support advanced node semiconductor production in a market that is geographically and politically separated from the markets ASML currently serves. A Chinese EUV machine does not need to match ASML's throughput, its resolution, or its reliability to be strategically decisive. It needs only to be good enough to allow Chinese foundries to manufacture chips at nodes that currently require ASML equipment. Good enough is a much lower bar than best in class. And good enough, in a market of 1.4 billion people supported by the full financial and institutional weight of the Chinese state, is potentially sufficient to sustain an entire domestic semiconductor ecosystem independent of ASML's products and the export control architecture built around them. That is what keeps ASML's leadership attentive, not a better machine. a sufficient one in the wrong hands, built behind a wall they cannot see over. What China actually announced, the Changchun Institute of Optics, Fine Mechanics and Physics, known within Chinese scientific circles as CIOMP, published findings in 2024 describing a domestically developed laser-produced plasma EUV light source generating radiation at 13.5 nanometers. This is the wavelength used by ASML's production EUV systems. The source power figures cited in the Chinese publications, while below the levels required for high-volume production lithography, as ASML currently defines it, represent a measurable and significant advance beyond what Chinese institutions had previously demonstrated publicly. The announcement was not a claim of full production-ready EUV lithography capability. It was a claim of demonstrated progress along the development path toward that capability at a pace that the publication timeline and the technical specificity of the results suggest is more advanced than Western analysts had been estimating. Independent verification of these specific claims is complicated by the nature of the publication venue and the absence of third-party testing. Chinese scientific publications, particularly those emerging from state-linked research institutes working on strategically sensitive technology, are not always structured to facilitate the kind of independent replication and external validation that Western scientific norms expect. This does not mean the claims are false. It means they require careful interpretation against the broader pattern of evidence rather than simple acceptance or simple dismissal. The broader pattern of evidence is, by any honest assessment, more concerning to Western semiconductor interests than the specific Changchun announcement taken in isolation. CIOMP is not a new or obscure institution improvising in a domain it has no background in. It is a 70-year-old research organization with a deep and documented history in precision optics, laser physics, and photonics that constitutes exactly the scientific foundation on which EUV source development is built. The institution has published peer-reviewed work on EUV relevant topics for over 2 decades. Its researchers have attended international conferences. Its patents have been cited by international competitors. The scientific foundation was visible. The industrial application is what surprised people who had been looking at the foundation without fully tracing where it led. The specific technical claims that have received the most attention concern source power, source stability, and the spectral purity of the 13.5 nanometer emission. All three are critical parameters for lithography applications. Source power determines throughput, how many wafers can be exposed per hour, which directly determines production economics. Source stability determines pattern fidelity, because a fluctuating source produces inconsistent exposure doses that degrade critical dimension uniformity across the wafer. Spectral purity determines how much out-of-band radiation reaches the wafer, because radiation outside the 13.5 nanometer band does not contribute to useful patterning, but does contribute to heating and contamination. China has demonstrated progress on all three parameters. It has not yet demonstrated production-level performance on any of them. The distance between those two statements is where the honest assessment of the situation lives. The physics they had to conquer. Generating EUV light at usable intensities is a physics problem that resisted serious engineering solutions for decades. Understanding what China has had to conquer to get to this point requires understanding why the problem is so hard. EUV radiation at 13.5 nanometers is generated by heating a small amount of tin, usually delivered as a microscopic droplet, to a temperature of approximately 500,000 degrees Celsius using a high-powered pulsed laser. At that temperature, the tin atoms lose electrons and become a highly ionized plasma that emits EUV radiation across a range of wavelengths. A set of precision mirrors arranged in a specific geometry collects the EUV emission from the plasma and directs it toward the optical system. This sounds straightforward when described in a single sentence. It is not straightforward. Every element of this description contains engineering problems that took ASML and its partners years to solve at production scale. The tin droplet delivery system must place droplets of precisely controlled size at precisely controlled positions in space at a rate of 50,000 droplets per second. The laser must intercept each droplet with sufficient precision and power to generate a plasma of consistent temperature and density. The plasma itself generates debris, fragments of tin that travel outward in all directions and will contaminate and degrade the optical surfaces that collect the EUV emission unless they are intercepted by a hydrogen gas curtain flowing continuously through the source chamber. The multi-layer mirrors that collect and direct the EUV light are engineered to reflect at 13.5 nanometers using alternating layers of molybdenum and silicon deposited with atomic scale thickness control across a mirror surface that must be polished to a smoothness measured in fractions of a nanometer. Each mirror reflects only about 70% of the incident EUV radiation. The optical system requires multiple mirrors in series. The total transmission through the system is therefore the product of multiple 70% reflectivities, which means collecting sufficient EUV power at the wafer plane requires a source of enormous raw output to compensate for the accumulated losses. China had to develop solutions to every one of these engineering challenges using domestic expertise, domestic materials, and domestic manufacturing capability that had never previously been required to perform at this level. The tin droplet generator, the high-power pulsed laser, the hydrogen curtain debris mitigation system, the multi-layer mirror deposition process, the vacuum system that maintains the pressures required for EUV propagation, each of these is a major engineering program in its own right. China is working on all of them simultaneously. The Changchun announcement suggests meaningful progress across several of these areas at a pace that the Western semiconductor policy community had not adequately incorporated into its planning assumptions. The supply chain they built in secret parallel to the source development work at institutions like CIOMP, China has been assembling a domestic supply chain for EUV adjacent components and materials that has proceeded largely below the radar of Western export control enforcement and competitive intelligence efforts. This supply chain does not yet constitute a complete domestic EUV ecosystem, but its existence and its current state of development are substantially more advanced than was understood even 2 years ago by the analysts and government officials responsible for tracking it. Chinese domestic production of high-purity tin, the consumable material at the heart of laser-produced plasma EUV sources, has expanded significantly in recent years. China is the world's largest tin producer and has invested in the purification and isotopic control processes required to produce EUV-grade tin at commercially relevant volumes. This is a materials science and process engineering challenge that most coverage of China's EUV program ignores entirely, because tin does not sound as technically impressive as multi-layer mirrors or high-power lasers. But running out of sufficiently pure tin is a perfectly capable way to stall an EUV program, regardless of how good everything else is. Domestic production of the high-power pulsed lasers required for EUV source excitation has advanced at companies including IFI's Chinese competitors and a cohort of state-backed laser technology developers in Wuhan, which has quietly developed into one of the world's significant centers of high-power laser research and production. The multi-layer mirror deposition technology required for EUV optics has been under development at the Tongji University National Laboratory for Condensed Matter Physics in Shanghai, which has published peer-reviewed results on molybdenum silicon multi-layer systems relevant to EUV applications over a period of years. The precision polishing and metrology capabilities required to manufacture EUV quality mirror substrates have been developed at institutions in Beijing and Chengdu, with long histories in precision optical manufacturing for defense and space applications. None of these individual threads constitutes a complete EUV supply chain on its own. Together, assembled into a coordinated development program with state-level funding and institutional coordination, they constitute the outline of a supply chain that did not exist a decade ago, and that is visibly more complete today than it was 3 years ago. The direction of travel is clear. The distance remaining is genuinely uncertain. This didn't come from nowhere. China's ability to make credible progress on EUV development rests on a scientific foundation built over 30 years of sustained investment in precision optics, laser physics, and photonics that the Western semiconductor industry has consistently underweighted in its assessment of Chinese technical capability. The assumption that China was a consumer of optical technology rather than a developer of it was comfortable, widely held, and significantly wrong. SciOmp itself was founded in 1952 and has operated continuously as one of China's premier precision optics research institutions for over 7 decades. Its researchers pioneered adaptive optics technology for China's astronomical observatory program, developed high-power laser systems for defense applications, and contributed to the optical systems used in China's Earth observation satellite program. These are not trivial scientific achievements that happened to share a building with the EUV program. They are directly relevant technical capabilities that provide exactly the foundation on which EUV optical system development is built. Adaptive optics expertise translates directly into EUV mirror alignment and wavefront control. High-power laser expertise translates directly into EUV source excitation system design. Precision optical fabrication expertise translates directly into mirror substrate manufacturing. The lineage is direct, and it is deep. Tongji University's work on multi-layer optical coatings for the extreme ultraviolet wavelength range goes back to the 1990s, when Chinese researchers began investigating EUV optics for synchrotron beamline applications, long before EUV lithography was a commercially relevant technology. This work produced a generation of researchers with hands-on experimental expertise in EUV optics that no amount of recruitment from the commercial sector could have quickly replicated. The Harbin Institute of Technology, Northwestern Polytechnical University, and the University of Science and Technology of China have all contributed relevant graduates and research outputs to the broader ecosystem of institutions now feeding into China's EUV development programs. This is the scientific infrastructure of a country that decided, a long time ago, to be serious about photonics. The semiconductor industry is only now fully confronting the consequences of that decision. What the verification problem means. Assessing China's EUV progress accurately is genuinely difficult, and the difficulty is not symmetrical. It cuts in both directions in ways that should make observers cautious about confident conclusions in either direction. Overstating China's EUV progress leads to policy overreaction, to investment misallocation, and to a narrative of inevitable Chinese technological dominance that is not supported by the evidence, and that can itself become strategically counterproductive by generating defeatism in the institutions that need to respond. China's EUV program is behind ASML's commercial systems by a margin that is real, substantial, and meaningful in practical production terms. A laboratory demonstration of a functional EUV light source is very far from a production-ready lithography system capable of exposing wafers at commercially viable throughput and with the pattern fidelity required for leading-edge semiconductor manufacturing. The gap between those two things is measured in years of engineering development and billions of dollars of investment, even when the basic science is demonstrated. Understating China's EUV progress, on the other hand, leads to exactly the kind of policy failure that produced the Huawei Mate 60 Pro surprise. The assumption that China was too far behind to matter, that the engineering challenges were too formidable, that the timeline to any relevant capability was too long to require urgent response was embedded in the Western semiconductor policy architecture and was wrong in ways that had immediate strategic consequences. The same assumption applied to EUV carries the same risk of being wrong in the same direction with consequences that would be significantly larger. The honest assessment of what the available evidence shows is this. China has demonstrated EUV light source generation at the relevant wavelength. China has demonstrated multilayer mirror fabrication capability relevant to EUV optical systems. China has assembled a broader research and supply chain ecosystem that is more complete than Western assessments had projected. China has not yet demonstrated a complete integrated EUV lithography system operating at production-relevant throughput and pattern fidelity. The distance between where China demonstrably is and where it needs to be for production-relevant EUV capability is real and should not be minimized. The pace at which that distance is being closed is faster than the Western semiconductor policy community was assuming. Both of those things are simultaneously true, and holding both of them in mind without collapsing into either complacency or panic is where the analytical challenge actually lives. The industry response. Nobody expected. The semiconductor equipment industry does not panic visibly. It is populated by engineers and executives who communicate in the careful, qualified language of people who have learned that public statements move markets and that precision matters. But underneath the careful language, the Changchun announcement and the broader trajectory of China's EUV program have produced responses that are visible to anyone paying close attention to where money is moving and where engineering priorities are shifting. ASML has accelerated its high-NA EUV program with a pace and a public emphasis that reflects, at least in part, a strategic calculation that staying as far ahead of any potential Chinese competitor as possible is the most durable form of competitive defense available. High-NA EUV, which uses mirrors with a higher numerical aperture to achieve finer resolution than current EUV systems, is a technology that extends the frontier of lithographic capability to nodes below 2 nanometers, a domain where the physics challenges facing any Chinese domestic development program are substantially more severe than those at the current EUV production node. Racing to the frontier is a reasonable strategic response to a challenger approaching from behind. ASML is running. Applied Materials, Lam Research, and Tokyo Electron, the major semiconductor equipment companies whose tools are used across the process flow before and after lithography, have all been investing in capabilities that reduce the total number of EUV exposures required per process layer. This investment, framed publicly as a cost reduction initiative for their existing customers, also has the effect of making EUV throughput limitations, which would be more severe in a first-generation Chinese domestic system, less limiting for the overall manufacturing process. This is either a coincidence or a strategic hedge. The equipment industry does not tend to make major R&D investments by coincidence. TSMC's ongoing investment in packaging technology, specifically in advanced three-dimensional chip stacking and heterogeneous integration, has the practical effect of extracting more compute performance from a given process node by connecting multiple chiplets manufactured at different nodes into a single high-performance package. This reduces the rate at which raw lithographic node advancement translates into end product performance advantage. A world where packaging innovation partially substitutes for lithographic node advancement is a world where a Chinese foundry operating at a one-generation node disadvantage due to EUV limitations can close more of the end product performance gap than the node disadvantage alone would suggest. TSMC is building exactly that world, which benefits its own customers today and simultaneously reduces the strategic impact of the EUV gap that Chinese manufacturers currently face. The geopolitical acceleration. China's EUV progress, even at its current pre-production stage, is reshaping the political and policy landscape around semiconductor technology in ways that are accelerating rather than stabilizing. The Biden administration's October 2023 export control expansion, which added restrictions on DUV equipment sales to Chinese customers that went beyond the original EUV-focused measures, was motivated in part by intelligence assessments of China's DUV workaround capabilities that had already been demonstrated by the Kirin 9000S chip. The next round of export control tightening, currently under active discussion in Washington, Brussels, and Tokyo, is being shaped by assessments of China's EUV progress that are more alarming than the assessments that informed the previous rounds. The policy is chasing the technology. The technology is not waiting for the policy to catch up. Allied coordination on semiconductor export controls remains imperfect and contested in ways that create genuine gaps in the control architecture. The Netherlands, home to ASML, has economic interests in its semiconductor equipment industry that create political friction around export control measures that directly reduce ASML's addressable market. Japan's semiconductor equipment companies, including Tokyo Electron and Shin-Etsu Chemical, face similar tensions between national security alignment with the United States and commercial interests in the Chinese market that generates significant revenue. South Korea, home to Samsung and SK Hynix, has enormous existing investments in Chinese manufacturing facilities that complicate its willingness to fully align with the most aggressive versions of American semiconductor decoupling policy. These tensions are real, and they are not going away. They are being managed imperfectly by allied governments that are trying to balance commercial interests, alliance obligations, and strategic imperatives that pull in different directions simultaneously. The CHIPS and Science Act investment in domestic American semiconductor manufacturing is the most significant response the United States has made to the broader semiconductor competition challenge, and it represents a genuine shift from the export control-only approach that characterized the initial policy response. But the fabs under construction in Arizona and Ohio will not reach full production capacity until the late 2020s. In a technology competition measured in 2 to 3 year cycles, that timeline gap matters. Where this ends, the end point of China's EUV development program, if it proceeds along its current trajectory with current levels of state support, is a domestic EUV lithography capability that is functionally sufficient to support advanced node semiconductor production for the Chinese domestic market. Not superior to ASML, not commercially competitive on the global export market in the near term, but sufficient. Sufficient is the word that matters here, because sufficient changes everything about the strategic landscape in ways that superior would merely confirm. A China with sufficient domestic EUV capability is a China whose semiconductor industry is no longer meaningfully constrained by Western export control architecture. The entire strategic theory of using technology access restriction to maintain a permanent and widening technology gap between Chinese and Western semiconductor manufacturing depends on the export controls remaining the binding constraint on Chinese progress. Once domestic EUV production removes that constraint, the binding limitation becomes Chinese engineering talent, Chinese process development experience, and Chinese capital allocation, all of which are resources that China possesses in substantial and growing quantities and that no export control regime can restrict. The timeline to that outcome is genuinely uncertain. Optimistic assessments within Chinese research institutions suggest production-relevant domestic EUV capability within 5 to 7 years. Independent Western assessments tend toward longer timelines, ranging from 8 to 15 years, while acknowledging that the pace of Chinese progress has consistently outrun Western projections in adjacent areas. The honest answer is that nobody knows with confidence, and the history of this competition suggests that confidence in long timelines is a form of strategic complacency that has already been punished once. What is not uncertain is the direction. China is building the one thing ASML feared most. It is building it systematically, with institutional seriousness, with state-scale resources and with the accumulated scientific foundation of 30 years of precision optics research that nobody outside a small circle of specialists was tracking carefully enough. The monopoly that ASML built over 3 decades at a cost of billions of euros and thousands of engineer years is facing its first genuinely credible challenge. And the company that is mounting that challenge is not a Western startup with venture capital and a clever idea. It is a civilization-scale engineering program backed by a state that has decided this outcome is non-negotiable. ASML knows this. The question now is whether everyone else figures it out before the window for a serious response closes.